Hi everyone, I'm back again for now. For today's video, we'll try to discuss what is trees. So trees represent the nodes connected by the edges. We will discuss binary tree or binary search tree specifically. So this binary tree is a special data structure used for data storage purposes. A binary tree has a special condition that each node can have a maximum of two children. A binary tree has the benefits of both an ordered array and a linked list. A search is as quick as an sorted array, and insertion or deletion operations are as fast as in linked list. So these are there are important terms for the trees. So path refers to the sequences of nodes along the edges of the tree. Root, the node of the top of the tree is called root. There is only one root per tree, and one path from the root node to any node, which is uh, the parent node and the child node. So parent, any node except the root node has one edge apart to a node called parent. The child the node below a given node connected by its edges downward is called its child node. Leaf, the node which does not have any child node is called the leaf node. Subtree, subtree represent the descendants of the node, which is the root and its subtree. Visiting refers to the checking values of the nodes, and control is in the node. Traversing means passing through the nodes in a specific order. The level of the node represent the generation of a node. If the root node is a level 0, then its next child node is a level 1, its grandchild is a level 2, and so on. Case represent the value of a node based on which a search operation is to be carried out for each node. There are we call this insert and deletion and the search operation for um, basic operation for a binary search tree, in where there can be performed on a binary search tree. Data structures are the following. As what I've said, inserts an element in a tree or create a tree. Searches an element in a tree per order traversal. Traverses a tree in a pre-order manner. In order traversal traverses a tree in an in-order manner. Post-order traversal refers to traverses a tree in a post-order manner. So pre-order, in-order, and post-order is just like as what we've been discussed. We already tackle about the infix and prefix and postfix conversion. It's the same as concept as this pre-order and order and post-order traversal. So have here insert operation and search operation in the traversal. So first we have here an in order traversal, leaf, root, and right. So in this concept, the in order traversal will traverse in order. The output will produce sorted keys values in ascending order. So for us to determine this value or keys, first in order traversal node, first the we first visited the root node, which is A, which is the first visit, and the subtree B, which is the first visit, and D, which is the first visit, and then returns to which already the second visit for the which is the second traverse order, which is the right. As long as the D already visit two times, we can display D here in our in order traversal of 3, which is D. Since B is already traversed by 1 and E traversed by 1, and it traversed second time, which is E. So we print E. Already visited B here, so already write B or display D in order traversal here. So already visited E node, which is E. Since I forgot this node has a null value, which is x. So so it's considered as a null. So after visiting D, we'll proceed to B, which is the second time, and let's go for E for the first time, and E it traverses to E again, which is the second time. The moment we visited two times, we will display the E here and in an order traversal manner. So let's go back to A. So we already visited A two times, so we will display A in order traversal of D3. Next, we'll go to our right sub 3. Since we already visited A two times, already displayed E here. So already next, then we'll proceed to our right sub 3. First, we visited sub KC, which is the first time. Already visited this first time. Next, we'll go to our left sub 3. Right sub 3 under the F. Already visited here. Already visited this for the first time. Here, we consider that F K node has a X, and already have a null value, which is X represented by X. So here, already visited F for the second time. So we display F into our in order traversal manner. Then C, we already visited C for the first time, and now we already visited C the second time. So the moment, as I said, the moment we visited the K nodes or K values of C, we will print C here. We will try to display C in our unordered traversal manner. Then next, for the first time, we visited G case. Then G, the moment we visited G the second time, I will print or display the G in an ordered traversal manner. Next, we will proceed to pre-order traversal. So this pre-order traversal, in this traversal method, the root node is visited first, then the left sub 3, and finally the right sub 3. Here, unlike from in-order traversal, pre-order traversal, you just need to visit for the first time. The moment we visited our root node A, it will be displayed. Next, our K node case B, or value case has value of B. So display B. Display D, since we already visited it. Since we already print the value of B, we will now proceed to our E, which will be displayed. And A, we have here A, since we already visited our root node A here and here. So we'll proceed to our right sub 3, which is the K has a value of C. So as I said, the moment we first visited the left sub 3 and the right sub 3, and each case will display the output of the pre-order traversal. So F, we said F, display F, and then next we visited to C. Since C we already display C, now we'll proceed to G here. Now that's it. That's our pre-order traversal, which is the root, left, and right. And now, in post-order traversal left and right, and note in this method, the root node is visited last, hence the name. First, we traverse the left sub 3 and the right sub 3, and finally the root node. So, since it says that our root node will be visited last, so we'll start from here. Our left sub 3, which is K value of B. So this, what I mean is the following post-order, we first B is also traverse post-order process goes on to all the nodes are visited the outpost of the post-order traversal. This day will be sorry for the misinterpretation. So here we, as it said, root node will be visited last. So we'll now proceed to our left sub 3, which has a value K of value of B. So first here, display B as our post-order traversal. Next is E. The next is B. Since it's already said that we will jump to our right sub 3, which is F. Next is our G. Next our C. For our K, C, K has a value of C. Next is the our last root node, which is A. Now we will try to create a presentation for a binary search tree, which is has a basic operation of insert, deletion, and search. And we'll try to find the height of our binary search tree, and we'll try to display the pre-order and in-order, pre-order, and post-order reversal in our code. And now we will try to create the code for our binary search tree method. Yeah. So first, I already created here a package and a main class for our binary search tree, and now I already declared our class node for our binary search tree. Now let's properly start our code, and I hope you can bear with me as I'm also learning this code, and I hope you will be patient. Now let's properly start. First, we have here a declared class for our BST class. Then we created a class node for a inner class node for representing a node for our binary search tree. And now we'll try to declare our integer variable named K and a node left and right. Now we'll try to create a constructor for our class node. Copy node data is equals to data, left is equals to right, right is equals to this line of code, this will be our constructor for our class node. And now let's try to create a root node for our binary search tree, and let's try to create a constructor class for our let's try to create a constructor class for our BST class. Root is equals to null, and after that I will try to as we initialize here our root is equals to null, or it doesn't have any value for our root at first. And now let's try to create a deletion method for our binary search tree. Void delete key. Inside this tree, let's try to create a call for our recursive delete method. So here, root is equals to delete recursive. This will be our recursive method. This will be another recursive method for our to delete a key from a binary search tree. So inside this inside this recursive method to delete a key, we have here two if else statement, else if statement, and if else statement. Now let's try to create the if statement at first. So if our root is null, then let's try to return the root. Return root. If our key is less than our root key, if that na just holding it equals it. Delete this first. Okay. Now let's try to create our else if statement. Let's try to create our else if statement. Okay, is greater than our root key. Is that right? Is that right? Is equals to equals to return that right? first, let me debug it first before proceeding to another method. So as I've said, this node, this recursive, this let's try to debug it first. This our delete k method for our class. So here we have here node delete recursive method. So node delete recursive node root. Okay. If root is equals to null, let's return root. If root is equals to null, if case if k is greater than root dot key, root dot right, supposed to delete that recursive root dot right. Forget the here, root dot right. Okay. Else if root that supposed to now return root that right. Else if root that right supposed to null, return root that and return that value. Root that right return that. And now let's try to proceed for our create mean value for our method here. Here we created a method for our mean value or for our minimum value. This is the method to find the minimum value of our binary search tree. Let's just try to create a integer minimum value where we need to return 0 for us this code to properly run. So here let's try to create a root key for our minimum value in where our min val is let's try to create a integer variable min val, which has the value of root that key. Now we try to create a while condition, which is root that left is not equals to null. Is min val is equals to root that left that key, and root is our root that left. Let's try to return the value of min val. Now let's try to create insert method for our insert method k for our binary search tree. Here, I try to create a void insert. Okay. What happened? Void insert. Void insert. Okay. Root is equals to insert recursive as what we've done for the deletion. We also call the recursive method for insert. So here equals to root and now it's time to create a node method for insert recursive. This was and key and call the and we will try to create here again another condition for us to insert a key to our binary search tree. Here try to create an if statement. If root is equals to null, root is equals to new node k. Let's return the root, and if else if k is less than our root k, if that to insert recursive, be sure to be details, little details in your this will be the deciding code for our this binary search tree. Maybe you call wrong spelling or either wrong punctuation or either wrong semicolon or another open bracket or close bracket. Root that left is equals to insert recursive root left and recursive insert is greater than root okay. Root that's right. Supposed to insert recursive root that's right. means that this block of code represents that we try to insert a key into our binary research, and through this node insert recursive node root is in key. This will be our recursive method for us to insert a key into the binary search tree. And now let's try to create a method to perform an in order traversal for the binary search tree. So we have here void in order recursive root. Let's try to create a recursive method for this in order method. So void in order recursive if root is not equal to null, in order recursive root method. Print or now we already created in order for our traversal for the search tree. Now let's try to create a pre-order a pre-order method for our pre-order traversal. Now let's try to create a recursive method for this pre-order. Pre-order recursive root is not equals to null. We print out a message for we print the print excuse us. Pre-order a recursive. So that's right. Pre-order recursive. Here we already created our pre-order traversal and in-order traversal, and the remaining is for the void I mean post-order traversal. So let's try to create a void. Let's try to create a method for our post-order traversal. Void post-order post-order traversal. Let's try to create a recursive method for our post order. Again, let's try to create each statement if root is not equals to null, and then post order recursive like that. And this one is put that right. Let's try to create this. And now we're done with our in order, pre-order, and post-order traversal method. And now let's proceed to the last task that was given to us to find the height of this binary search tree. Now let's try to create binary search tree. Let's try to create the method for us to find the height of the binary search tree. Now, height return recursive let's try to create a recursive method for this height recursive height recursive this recursive method explains this will the one who will calculate the height for our binary search tree. So if root is equals to null, return 0. If not, then plus equals to 5. First is root dot return. What next? Fine. Or we've done with creating height for us to determine the height for our linear search tree, and now let's proceed for main class. We're try to call this method, and let's try to see the outcome of this code. And now here I already instanced BST class, where this BST class will be called or will be triggered upon calling those sorry for that. Those BST class under the BST class will be called this and this class. After instantiating this BST class into we call the object, which is BST. Now we'll try to create let's try to insert an element inside our binary search state, which is bst.insert. First, let me copy this. Let's try to put a value inside this key. Now let's try to perform the in order traversal for our binary search tree. Now let's try to create the system.out. Now let's try to perform a delete key inside our system out that way. my in order method will be called now let's try to create another deletion. If we delete E45, what will be our new node after deleting E45? Node to checker. Now let's try to print our traversal from in order, pre-order, and post-order traversal. Here we'll try to create print for pre-order traversal. Let's do that. Pre-order. And now let's try to print the height of now let's try to run this code, and I hope we will get a satisfactory output for this code. The height of our get the correct height of our BSD. And now let's start with creating our let's try to debug the height first before proceeding with other code. So the height of BSD, height. Requiring that percent, now after debugging it, and now we have here the height of our best T. We're defining the height of our best T using the height method here, and this will be the one our pre-order and post-order traversal, and our an in-order traversal which has been called here. And the first part is the best created with the input data left and root and right according to our PowerPoint. Left and root and right is equals to our in order traversal. And here after deleting key node left node of 12, we have here 10 14 and unupdated value 7 10 15 7 10 45 7 10 and so on. So I hope this code, I hope this evening you learn something, and I hope thank you for being so patient, and up to this point thank you for this opportunity to share my thoughts about this code. So thank you, and that's all.